Thank you. Thank you. Hello, AoT. Let's see. Do it that way. All right. So this is a fantastic age for astronomy. We've got multiple telescopes in space. We can see back billions of light years to the earliest days of the universe. We're detecting gravitational waves from black holes merging. And yet we are still making discoveries very close to home in our basically astronomical backyard. So we've known for decades now that the sun is a normal star in a fairly typical region of a pretty common type spiral galaxy. And that doesn't sound nearly as exciting as merging black holes or exoplanets, things like that. But with all that normalness, our solar neighborhood is representative. It's a common type of place in the universe as far as we can tell. And so studying what's near us teaches us about the common things, the things that are the most likely to find in the universe. So what are those things? When I say solar neighborhood, I mean not the planets, but outside of our solar system in the nearby area of our galaxy. And what it's full of is stars. There's a little bit of gas out there, but mostly it's dominated by stars. And if you look up on a starry night, see a rich star field like this, one of the first things that may pop out at you is colors. There's blue stars, there's white stars, there's yellow stars, there's reddish stars. You can immediately tell there are different kinds of stars. What can we learn about this? So I'm going to show you a tool that astronomers have been using for more than 100 years. If you've ever taken an astronomy class, this is guaranteed to be in it, and it's a tool that astronomers still use to this day, and it's the Hertzsprung-Russell diagram, or HR diagram. And it's a simple graph where two axes are luminosity, that's how bright a star is intrinsically, just how much light it's putting out, and temperature, which you can measure from a star normally by analyzing the spectrum of its light. And so you find a star, you measure its luminosity, you measure its temperature, and you put it on the graph. And there's the sun, for example. Other stars you may have heard of, the Rigel and Betelgeuse are both in Orion. There is Polaris, the North Star. And if you do this for lots of stars, patterns emerge. One pattern that shows up right away is that the blue stars are all over here on the left, where there are high temperatures. The reddish stars are over here on the right with low temperatures. I realize that the axis is backwards, but it's been that way for 100 years, so sorry, we're stuck with that. Hot stars on the left, and those are the bluish stars. Cool stars on the right, those are the reddish stars. And when I say cool, 4,000 Kelvin is enough to melt any metal in the periodic table. So it's still hot, but relatively cool relative to the other ones. Another thing you can notice is that there are definite patterns here. There are some places where stars cluster, like the giant stars have these groups on the upper right. There's this long strip from left down to the bottom right, which is called the main sequence. And then there are also empty spaces. There are places where we don't find any stars. And just this basic diagram has helped astronomers for a century to understand the physics and structure of stars. In particular, that main sequence contains about 90% of the stars that we know of, roughly. It's where stars spend most of their lives fusing hydrogen into helium. And when they run out of hydrogen to fuse in their cores, they puff up and they get bigger and cooler and they become giant stars. And most of those stars puff out the outer layers, and you're left with just a very hot core that is also very small, so you get hot, faint stars, which are called white dwarfs. Now, I'm going to show you another version of this that maybe looks a little prettier, has a little more detail to it, although it's still a cartoon, but it shows those same groups of stars. And here's the sun. I'll show you the location on it, very normal main sequence star. And we've also got these letters across the bottom, which are the spectral types. They're letters that astronomers use to categorize stars by features in their spectra, which are directly connected to the temperature. O stars are the hottest stars, M stars are the coolest stars. The letters are in this weird sequence, basically because the letters were originally signed based on a spectral feature, the strength of hydrogen absorption lines. And later on, astronomers, in particular Annie Jump Cannon, realized that that was kind of a strange way to categorize it. How about sorting them by temperature, and ended up with this sequence of letters there. Okay, so do we see all these kinds of stars in the sky when we look up? Going to show you, not a cartoon, but an actual plot of an HR diagram of stars that we can see with our naked eye. And I mean like West Texas kind of naked eye where it's really dark, not downtown Austin. But this is what you see here. Does that look like the HR diagram? Well, I will show you where the sun is located on here, which is right about there. Down near the bottom, not so much in the middle. And that's because to the naked eye, we can only see brighter stars, the ones in the upper part of the diagram. So going back to this HR diagram, basically all the stars down there on the bottom, we can't see any of them with the naked eye. So if we didn't have telescopes, we wouldn't know about white dwarf stars. We wouldn't know about the cool M red dwarf stars. So what about, these are the stars we can see. Is that the same as the stars that are close to us, that are in our neighborhood? So to explain this, I'm going to give a little more specific definition of what in the solar neighborhood means. My solar neighborhood is a bubble around the sun that includes everything out to 10 parsecs. What is a parsec? Well, if you're not a Star Wars fan, you may never have heard of it. If you are a Star Wars fan, the definition you know is wrong. So, parsec is a measure of distance that astronomers can actually measure directly. And to do that, this is what you do. Now, little demonstration. You can demonstrate this for yourself. There's that orange star up on the screen there. And think of that as a way distant background star. And then if you hold up your finger and close one eye and cover up that star from your point of view with your finger, and then close the eye and open the other eye and blink back and forth like that, you can see it looks like your finger is moving. Okay? So that's because your eyes are actually in two different places, looking at something way far away, and so things nearby look like they're moving. So astronomers do this to measure the distance to stars, but not two eyes, not two telescopes, but the Earth in one part of its orbit, and 6 months later, the Earth on the other side of its orbit. So those are the 2 points of view. And with those 2 points of view, you can see stars that are closer to us moving back and forth a little bit with respect to the background. By a little bit, I mean, for example, about an arc second at most. That's 1/60th of 1/60th of a degree. It's about the apparent size of a dime, 2.5 miles away. It's tiny, but we can do it. We can even do better than that. And we can measure distances to at least the nearby stars that way. 1 parsec is the distance away something is if it's that movement back and forth is 1 arc second. It's about 3.26 light years, which is also kind of a meaningless number. So to give you a better sense, the closest star to us is about 1.2 parsecs away. And in general, on average in our galaxy, the distance between stars is about a parsec. So that's a sense of scale. Galaxy is very big. It's about 30,000 parsecs across. It's a useful unit for astronomers because of its connection to the stars. Okay, so back to the neighborhood. The solar neighborhood is a sphere that's a radius 10 parsecs. So everything within 10 parsecs of our solar system. That's big enough to include several hundred stars, so it gives us a picture of what our galaxy looks like in general. So what stars do we see inside that solar neighborhood? Well, here's the HR diagram for that volume of space. This is from the Recons group. This is a research group based in Atlanta that's been measuring parallaxes to nearby stars for more than 20 years. And they tell us that this is the HR diagram. Does that look the same? Let me point out the sun to you. Whoops, there we go. So what we learn here is that actually most of the stars in our neighborhood are pretty faint. And in fact, they're the stars that we can't even see with our naked eye. So going back to that HR diagram again, this is basically the solar neighborhood. We don't have any of the giant stars, the super bright ones, but we do have a lot of stars that we can't even see with our naked eye. All the M dwarfs that are there are invisible unless you have a telescope. And in fact, there are even fainter things that are not on this HR diagram, which are brown dwarfs. So here we've got M dwarfs, which are the coolest stars, and then even fainter things, which collectively are called brown dwarfs. These are similar to stars in that they are big balls of gas that get really hot when they collapse down to get into a ball, but they don't have enough mass. They're less than about 7% of the mass of the sun, so they don't get hot and pressured enough in their cores to start a fusion reaction. They just kind of cool down slowly over billions of years. But they're out there, and they have something to teach us. I'll get into that in a second. But knowing that there's brown dwarfs are there, I should point out also, the temperatures of them go down from the coolest stars down to the temperatures of our giant planets, which are pretty icy. Freezing temperature is about 273 Kelvin. So their room temperature is about 300 Kelvin. So getting even colder than temperatures on the Earth. So how many of these are there? I'm going to show you now the census, and this is as of yesterday, of stars in that 10 parsec sphere in our neighborhood. And this is what it looks like. So we've got some white dwarfs, and then we have no really hot stars at all, and a few of the cooler stars, and suddenly a whole ton of M dwarfs. So reminder, hot stars, there's none of them. Cool stars and brown dwarfs over on the right, and here's the line dividing them. And there's this enormous spike of the cool reddish stars, the M dwarfs. So, and this is something that we have found not only in our neighborhood, but looking around in other parts of the galaxy. The universe just likes to make M dwarfs, likes to make cool, small stars that we can't even see with our naked eye, even when they're in our backyard. Kind of wacky, isn't it? All right, now is this the whole story? Have we found all the things? Is this the complete picture? I'm going to show you, I'm going to highlight in white on each of those bars the things that have been found in the last 9 years. Okay, so we've already found the bright stars. There's nothing new there. These are, it would be hard to miss those. These are the bright ones that pop out at you, the ones you can see from downtown Austin. But we're still finding the cool reddish stars. There are probably not that many more out there to find, but we haven't found them all yet. And the brown dwarfs, there are absolutely more out there that we have not found yet. These coolest ones, these Y dwarfs, which are getting towards room temperature, all have been found within the last 10 years. And there are certainly more out there. Let me give you a couple examples. On the left, Lumen 16 is actually a binary brown dwarf, two of them orbiting each other. Way cool. It was discovered 6 years ago, and it is 2 parsecs away. That makes it the third closest system of stars or brown dwarfs to the sun. And we didn't know about it until 6 years ago. There's a story behind it. I don't have time now, but feel free to ask if you'd like. WISE 0855, that's the moving one in this little animation here. That was discovered the next year, actually by the same guy, Kevin Luman. He's good at this. It's only 2.2 parsecs away. It is really cold and faint. It's colder than freezing, 250 Kelvin. And it is the coldest brown dwarf we have ever found. And if it were at 4 parsecs, we would never have detected it. It's just too faint. I believe it's the tip of an iceberg. There are a lot of these cold, faint brown dwarfs out there that we just have not found yet. And they hold an answer, a secret answer, to a big question for astronomers, which is when the galaxy makes a batch of stars and brown dwarfs, what's the distribution of masses? How many massive stars, how many medium, how many small stars, how many brown dwarfs? We've got that. We understand it fairly well for more massive stars, but we just don't know yet for brown dwarfs how many the galaxy will tend to make at a time. Does it make a lot of the lowest mass ones that get really cold? Does it make more of the kind of intermediate ones? And if we knew more about that, we would have better insight into the physics of star formation, which continues to puzzle us and continues to be a big area of research. So, start to wrap up here, but I want to highlight a little bit what is not within 10 parsecs. What didn't we see in our neighborhood? Well, none of the giant stars, none of the hot stars. So they're more rare. They certainly exist, but they're just not as common. Cool things that you see through a backyard telescope. Star clusters, newly forming stars, nebulae, none of those in our neighborhood. Again, they certainly are out there. They're just not as common as these cool stars and brown dwarfs. So, lessons from looking at our neighborhood to learn what the universe is like. There's a huge range of luminosity among stars. The very brightest ones are 1 trillion times brighter than the faintest ones. Hot stars, giant stars, nebulae, these are rare. We see a lot of them in the sky because they're very, very bright, so we can see them a long way away, but they're just not that common, especially not compared to the coolest stars. That's what the universe likes to make. That tells us something about the physics. We haven't figured out exactly what yet, but something about how the universe works. And those stars are very faint. It's amazing that most of the objects that are within our neighborhood we can't even see with our naked eye. And we're still discovering some of those. And they hold the key to understanding something about the way that our universe works. And I realize I didn't mention planets, and someone's going to ask. Besides the 8 in our solar system, there's about 35 exoplanets within 10 parsecs. That is not nearly the whole truth, because we are not able to detect most of them. Our technology just isn't there yet. So there's going to probably a few hundred exoplanets within 10 parsecs. Thanks.
Thank you, Dr. Darkstar. So we got some time for some questions. Sir, yeah, the one behind you.
Okay. Do some of the stars we can't see with our naked eye account for dark matter? Yeah. That was definitely a theory that has now basically been discarded, but at least a hypothesis several decades ago when we started finding M dwarfs and brown dwarfs. They said maybe there's so many of them that they are the dark matter. It turns out that there's not nearly enough. So, but it was absolutely considered for a while.
Standing by the bar?
So there are about 250 billion stars in the Milky Way. Do you expect that number to go a lot higher once we discover more of these cool stars? Yeah, so 250 billion stars in the galaxy. I've heard that estimate too. Do we expect there to be a lot more of them? Probably that number is roughly accurate. Maybe it'll go from 250 to 300 billion. You know, in astronomy terms, that's nothing. That's whatever. But brown dwarfs, I would say, we still don't know how many are out there. That could change by up to an order of magnitude.
Right there. Yes. Yeah.
Does the number of brown dwarfs give you any sense of the age of the galaxy, or is that just a factor of like what we tend to make stuff that's there?
Okay, so the number of brown dwarfs out there give us a sense of the age of the galaxy? Age is a tricky question about brown dwarfs, so I'll give you a little bit of a hint of that. When you look at a star or a brown dwarf, it's easy to measure how bright it is. It's harder but very possible to measure how far away it is. That's parallax. But it does not tell you its age, and it does not tell you its mass. Now for stars, we've worked out a lot of theories that say, well, if it's so bright and this color, we can get the mass pretty much right. And in some cases, we can even pin down the age. But the ages are slippery because they don't hold up signs saying what their age is. And they don't change a lot over time in most cases, which makes it tricky to figure out ages. Brown dwarfs are worse. They cool down over time. So you can't even figure out looking at one, well, if it could be low mass and young and this bright, or it could be high mass and old. So there is information about age in the brown dwarfs, but we just don't really have a good handle on it yet.
Right there.
Do you think there's categories of stars that might be cooler than brown dwarfs or higher than white dwarfs that we just haven't found yet?
Okay, good question. Are there categories of stars that are cooler than brown dwarfs or hotter than white dwarfs? On the hot end, first of all, there is. This is not so much my expertise, but I think there is debate about how massive and hot a star can get. There's a thought that it depends a little bit on the composition of the star, what exactly is in it. But probably the hottest white dwarfs that we can see are about as hot as it can get. Somebody here, correct me if I'm wrong on that. As for the cold end of things, well, there's a lower limit, which is 0 Kelvin. Can the universe actually make something that's that cold? The brown dwarfs that the universe has made may not have had the chance to get down near to 0 Kelvin yet. And one of the questions, big questions about that distribution of masses when you make a bunch of brown dwarfs is, how low can star formation go? What's the smallest, lowest mass thing that the star formation can possibly make? And that lowest mass thing is going to get cold the most quickly. And that would kind of set the lower limit. It's possible that it's as low as the planets in our solar system, but we don't know yet.
Last question.
Is there an international registry of all these stars that all countries agree to? And is there cooperation between the systems?
Okay. Is there an international registry of all these stars that different countries agree on? There is no, well, let's see. I'm not aware of any sort of official international registry. There is an International Astronomical Union that organizes a lot of information and sets definitions. And the IAU may have a catalog somewhere. Astronomers tend to use catalogs that have been developed by earlier astronomers. And so there are multiple ones that many people use. There are also catalogs of stars and other things that have been produced by sky surveys, where a telescope just observes the sky for a while and then produces a catalog of literally a billion objects. So we use things like that. And most of that is available to everyone. So it sort of works more, I guess it's more of a wiki kind of approach than one institution having a register.
Okay, great. Thank you, Dr. Darkstar. He'll be around for